Okay, good. Ooh, all right. So let me start my talk with one of the most stupendous achievements that AI has achieved recently, which was have you heard of this AlphaZero machine that DeepMind and Google built? Anybody here? Yeah, cool. Yeah, this is like amazing stuff, right? So for a long time now, we know that machines are really good at chess and games of that kind, and Magnus Carlsen has the yellow ratings here. Magnus Carlsen is around 2882, and the best computer software for playing chess is called Stockfish, and it's estimated at 3441. So humans are no match for the machines here, right? And what happened with AlphaZero was something very unique and special in that it was a machine, it was an algorithm that did not have any kind of input from the humans. Stockfish and other chess programs have a lot of heuristics built in through human experts who have analyzed lots and lots of games, and those rules are inside, and then with brute force computing power, you are able to overcome humans. But AlphaZero started from scratch. It just had the set of rules of chess. It just needed to know what is a checkmate and what are the rules of movement of the various chess pieces. And just with that knowledge, and purely by self-play, by playing against itself continuously, it managed to beat the best algorithm out there, which was created by humans. So this is an amazing achievement of AI, and pretty stunning at that, right? So this is where the systems and the progress is going towards, right? And it's not just in games of intellectual type where you want to play chess and there is a fixed rules and then you just need to beat it. But if you look at things like creativity, which are traditionally the domain of humans, they're getting closer and closer. So can somebody tell me which is a human drawn illustration and which is a machine drawn illustration? Any guesses? First is a human or machine? Okay, so there is a disagreement. That's the point, right? The first one is actually a machine generated, and the second one is a human painter who drew it. So it's fantastic. It just starts painting pixels and creating very interesting works of art, right? And a few more examples of such computational creativity, right? So this is a paper that came out in 2015 or so on the left, where you're given the picture of a lion and another piece of art, and the question that you're posing to the machine is that, can you make the lion in the style of the artwork? And it produces a very convincing illustration, right? And the point that I'm making here is that there are no rules. There is no set rules of what constitutes a good picture, but it's able to do a pretty good job. And on the right, you have abstract art that has been created through a machine learning algorithm called generative adversarial networks. And these have been, you put a survey to a lot of people saying that how good is it, how close is it to a human creativity, and then people picked all these things up as something, as a very good creative output from some humans, right? And if I need to convince you further, if you look at this, right, this is the latest work from NVIDIA, where from a pure random number, the machine is able to generate these synthetic faces. Notice that it's got all the details of the human faces represented there. There are some small problems here and there. If you look at the middle person's earrings, it's kind of slightly blurry, but beyond that, it's pretty stunning, right? And the way it does it is that you pump in a random number into this machine, and out will pop an image. You put another random number, another image comes out, right? So we are getting, the machines are getting really powerful, right? And so stunning stuff, right? So how did this all happen here? So I want to, it's not as if it just, things started happening the last 2 years and nothing happened before that. I really the whole aspect of machine learning goes back quite a few decades or centuries, right? So we can always start, everything can go back to Aristotle and Aryabhatta or something. But indeed, we can trace something to Gauss almost immediately. I mean, machine learning is a branch of statistics, and Gauss had some interesting things like normal distribution that we all use. It's called Gaussian distribution. And other important thing is that he's reported to have actually invented the first linear regression, right? So you get a bunch of points and you fit a line. So it was invented by Gauss, and that's one of the workhorses of machine learning that we use again and again. The other big, it's my interpretation of how the historical arc of machine learning went. So other people might have different interpretations. But I think the second big advance, I would say, was Hilbert, who asked the question about what it means to have a mechanical procedure to verify proofs. And the solution given by Alan Turing, which formalized the notion of an algorithm, was the other big advance that happened. Because the moment you have a formalized notion of what a mechanical procedure is, the next immediate question is that can you make a mechanical procedure to do the kind of things that humans do? Can you make a mechanical procedure that will learn on its own, right? So this was, I think, the arc that I would trace. And by 1950s, the field of machine learning was kind of firmly afoot, right? So let me get, as I go down, I'll get more and more precise about what we mean by machine learning. So if you go on the web and ask what is machine learning, this is the best definition that you would get, and it's a pretty good definition at that, right? So a program is said to be a learning machine, which learns from some experience E with respect to some class of tasks, right? You're supposed to give a set of tasks, you're supposed to give some experience, and there is a certain performance measurement of how well a task has been accomplished, right? If you have these three things, then you can feed back the performance measurement back to your learning program, and it starts improving in its performance. Then you are supposed to have a machine learning program, right? This is a definition that subsumes a lot of different types of machine learning, and pretty good definition, and more operational definition than simply saying machine should learn, right? It should learn with respect to certain data, and with respect to certain tasks, and with respect to certain performance indicators, right? Now let me get a little more detailed, and one instance of how this definition can be implemented. And so here there's a lot of things going on here, but I would focus your attention on the right panel. So first of all, the data or the experience first has to be represented as a set of numbers, right? You can't have data abstractly. It has to be converted into something numerical, right? And the learning machine's task is essentially the task of taking your input set of numbers and producing an output, right? And that output can be the output can be measured in terms of its how close it is to the truth, right? So this is a more operational definition. And if you see on the top, the animation that I'm showing is that you have your input data, the pink points, those are your data or the experience that you have measured, right? And there is a specific kind of learning machine called a neural network, which is there in the black, and you can initially see that it is performing very poorly at approximating the pink, the true function there. And as time goes by and it keeps on looking at this data again and again, you find that the mean squared error, which is how you're measuring the approximation error, it keeps dropping, and you can see that it gets closer and closer to the actual function. So this is pretty much connected to the lecture that you just heard previously, where we are talking about convergence and what it means to converge, and I can bring it all back here. So here, instead of looking at convergence of sequences, you are looking at convergence of functions, right? So you could think that it is a function analysis problem rather, right? And that's the thing we have here. And if you look at the learning rate again, so the convergence is not It's not a uniform convergence. It goes up and down, and that's very well illustrated. And it's a very common thing that initially the approximation seems to be good, then it actually worsens, but over time it kind of drops down to the desired level. Okay, so please feel free to interrupt me if I'm not making sense or if there is something that you want to address. All right. So let me get down a little bit more into what a neural network is. There are other kinds of machine learning, but I'm pretty much biased to neural networks, so you'll hear me talk about this a lot. Right? So the inspiration for a neural network comes from directly from our brains, because we are learning machines, and we have the basic unit of our learning is a neuron. And if you look at it, it's got a central unit, it's got a bunch of inputs coming into it, and it's got an output or multiple outputs, which are then shipped out to other neurons, right? And this whole neurons are connected in a complicated circuit in our brain, and somehow this architecture enables brains to learn from experiences pretty fast, right? So a mathematical abstraction of the neuron was made a long time ago, 1950s, right? And it said pretty much what I said. So down you see that there is a abstraction of it. There is a neuron which has a bunch of inputs, right? And the inputs are weighted. So inside the ellipse, what you're doing is you're doing a weighted sum of the inputs, and then you're applying one nonlinearity, either a sigmoid or something even simpler, and you get an output, and then you fan it out to other neurons, right? And you take such individual neurons. In the right, you see this picture where each circle represents a single neuron, and you interconnect them in myriad ways, and you put your input in the front, and you get the output at the right. So here you can see that the input is actually an image. The image is an interesting object because it is a set of pixels. It is already they are all real numbers, right? So you can just stick them as inputs into your machine, and then there are these weights which will learn all kinds of interesting things, and right at the output you can have your desired learning task, which could be recognize faces, or classify cats versus dogs, or so on, or whatever that you want, right? So this is the basic architecture of a neural network. Is it all too basic to you guys, or is it okay? Have you heard of these things before? Okay, all right. Or should I slow? You can stop and ask me any questions. All clear till now? Okay, all right. All right. So now I just told you about the architecture. I never told you how it is learning actually. Where is the learning involved? Are we just hard coding these weights? Are we just setting some weights to the input and output? No, that's not the way. We wanted to learn these weights. We want to learn these weights that will make it accomplish the task, right? So this is a representation. So you got a forward pass. This is what you would expect when the machine has learned. So you put in an input, which are pixels. You got layers, and then you got some kind of a nonlinearity, and then there is an output. The output is always class probabilities. Let's take a very simple example here, which is like cats versus dogs. That's your network's whole idea, is to say that if I put in an image, then it should tell me whether it's a cat or a dog, right? Two classes. So it needs to output a probability for whether it's a cat or a dog, right? So if you initialize your weights at random, and then you put in an image, then you'll get some random output, right? But the interesting thing is that you actually know what the truth is. You got a bunch of data points, labeled images of dogs, labeled images of cats. So if you put in a cat, and it gives you a kind of 50-50 or some random number over there, but you have the truth, which is that the blue one is very high and the red one is negligible. You have this truth, right? And you can actually compute an error function, a differentiable error function, based upon two probability densities. And now it's a simple matter to apply the chain rule to propagate the loss back, right? So in the first layer, what I have shown here is that there is this bunch of weights. So you take the loss function, you differentiate with respect to the initial set of weights, right? And you'll get the gradient you'll get a direction in which you will have to change those weights in order to minimize the loss. Right? And you make those changes, and those are the ones that are showing in slightly dark green. And you can iterate this. So now you know how to change the first set of weights. Right? Then you can go and ask, how should I change my second set of weights? So it is just a chain rule going backwards. Right? And it will tell me how to change the second set of weights in these layers. And then the third one with respect to the second layer, and so on. So I keep doing this, I keep doing this, and eventually what will happen is that the weights are set in such a way that for the given training set of cats and dogs, it's always going to give you the right answer. Right? It's pretty handful, so I'll stop. Is that a theorem? Is that a theorem? Yeah. No. So that's a great question. So it is not really a theorem, right? So you cannot, or at least we don't know. So these are, you ask the right question here. So much of this is kind of black art here. It converges. What are the functions for which this can converge? What are the functions for which such a thing works is very unknown. Or is this the only way to optimize the weights? We don't know any of those answers yet. What we do know is that these neural networks can approximate any function at any arbitrary accuracy. Whether a function can learn the set of weights is an open question. Whether this gadget has the capacity to approximate, that is well known. Yes, it can approximate. There was a question, yeah.
So, are you defining the edges before itself?
Yes, you have to define the edges before. You got to fix an architecture, and then you run this algorithm again and again. And that's another art that different problems will have a different architecture, which architecture to choose. So these are very open problems, really.
Are there stuff that fix the edges themselves, as in they learn which edges to fix?
Right. Yeah. So you come directly to my last part of the talk. So yes, so there are many ways. There are things that you can do So the question was, are these architectures fixed in advance? And then you optimize, or is there a way to learn the right architecture or the right interconnection beforehand? It is an open problem, and there are lots of startups trying to solve this very thing, right? And make any progress there, it's going to be of great interest to all of us. All right, let me go ahead. Okay. So a very brief chronology, and then I will come back to just a bunch of things. So you can see that somewhere between 1950s, we know about how to do all this in the 1950s. Rosenblatt, McCulloch-Pitts, and so on, right? And the backpropagation algorithm that I just defined was known by at least from 1986, right? And in between, there was a big AI winter where nothing happened between 1969 to 95. People kind of gave up on these neural networks because it was not able to, even though theoretically it was supposed to work, nothing worked in practice. So people abandoned it, and then they went to other things like random forest, support vector machines, and all that, which we use all the time, but that's not the scope of the talk today, right? And somewhere along the way, around 2012, right? Things changed dramatically. Before that, it was all wishy-washy. 2012, there is a very famous computer vision task called ImageNet Classification Challenge. So there's a Stanford professor, Fei-Fei Li, who collected millions of images and made people label them into 1,000 categories. So he collected a 1,000 category ontology, millions of images, got people to label what is in that image. Right? Now, this data set was an interesting thing, and the competition was that can you build an algorithm that, given an image, will be able to predict which of the 1,000 classes this image belonged to, right? And the entire computer vision community jumped on it, and there was no neural networks before 2012, or it was there, but nobody was looking at it. They tried all kinds of hacks, and I was one of them. So we try all kinds of things, right? Lots of heuristics, lots of fun to math. I don't know. So we used Yeah, we would use some manifold theory and whatnot, but it was always iffy. 2012, there were a few people from University of Toronto who took this neural network approach. They just took this entire data set. They had a pretty heavy architecture, and then they just dumbly followed the backpropagation algorithm that I talked about, and it beat the hell out of every other system out there. There was a 38% drop in the image classification error. This is like stupendous. I don't know how to give you the sense of the change that was. It was like there was some 100-meter race, and there was Usain Bolt is doing some 9.6 or something, and then somebody dropped it to 8. Then it's a pretty amazing thing, right? So that's what happened. And after that, there was no looking back. The entire community wholesale changed from the older machine learning paradigms into neural networks, and that's where we are today, and that's advances that I just showed you before. So just a couple of things. So since I'm from the industry, I'm going to talk about what's changed. Why is it all happening now? Why didn't it happen in the 1950s, right? So a couple of things. First is that 1950s and even early 2000s, we didn't have the computing power, right? And especially there was a new thing called the graphics computing, GPUs, or graphical processing units, which are used by gamers, right? And then so if you want some realistic rendering of graphics on your screen, or if you want some very interesting effects, then you use these graphics processing units. The thing about this is that it's got like 3,000 cores, 7,000 cores, and so on. It's not like one single core, and all the cores are set up so that they can perform an operation repeatedly, right? And this was a game changer. And once it was extremely useful and easy to implement these backpropagation algorithms in GPU. And we could actually take this million examples, pass them through this over a period of a day or two, and get some output out of that. So that changed. And the second thing is that there is this huge thing about cloud computing. There's a lot of data that is available on the cloud. You can pick up any machine, not just data, just computing power on the cloud, like Amazon, Azure, and all. You don't have to invest in physical hardware anymore. You can just hire them out, and that makes experimentation easier, right? And because of this mobility, there was another thing is that you had these mobile phones, which everybody now has, and we are sending out streams and streams of data to our providers and the other to carriers and application providers. And there was a need to capture all this data and make some use out of that. So there's a business reason for looking more into this deep learning architectures. And finally, we are also looking in the future or the near future about ASIC or FPGA or neuromorphic chips that are coming. So computing changed dramatically between the early years and 2012, and it's accelerating pretty fast. Right? The other thing is there's a huge drop in the storage costs. Right? And there's larger RAMs. Nowadays, you can have 1 terabyte RAM. It's no big deal. Right? So we can use them, and algorithms that were inconceivable to run are now possible. Right? And finally, I just talked about this data collection. Like data collection is being done by industries across the board, and because data, as somebody said, is the new oil, and data helps us serve the customers better and make more money out of them. So that's an important piece of it. And there's the crowdsourcing platforms and a lot of open data being available for research. That is also contributing to that. The other thing that I want to touch upon is that algorithms, deep learning resurgence has happened. There has been success in commercial settings, so companies are investing heavily in that. And the difference between earlier and now is that the research happens in the open. All the algorithms are pretty much published on arXiv the moment it's done. Yeah. Okay, and the frameworks, the developer frameworks are all open source, and we have open source distributed systems. We talked about the cloud computing earlier, and you have in-memory databases, large-scale databases. So all these things being in the open source helped a lot. And anybody can just spin up an instance and then start your deep learning work. Most of your infrastructure is available to you. Right? And I'll just briefly touch upon some of the machine learning systems in common use. I think machine learning touches all of our lives more than you can imagine. It's so prevalent that the cartoon there tells you that you can see recommendation systems being used across the board. You go on to Amazon or any e-commerce site and you see this thing saying that people who viewed this, or this is something nice, personalized for you. These are coming from algorithms, right? And more often than not, earlier it used to be non-neural network. Nowadays, there is a lot of neural networks behind the scenes producing these recommendations. The Facebook feed is in some sense a recommendation system. It tries to figure out what is the interesting content for you, right? And then produces that. It has to compute the right set of content very fast, continuously for all of you. You got vacuum cleaners, Roomba and others who are able to make sense of the room and then figure out what to clean and what not. Voice recognition has been a huge success. You can talk to your phones today and you can say, okay, Google, and then it understands you pretty much perfectly. Behind the scenes, there is a large neural network that takes your voice into account and then converts it into English or whatever language it is. And there is a semantic natural language understanding unit which figures out what exactly you are trying to say and then takes an action. Right? It's pretty good. If you look at Amazon's Echo, it's one of the fastest growing items in Amazon, and so that also does the same thing. Language translation, we would have all seen Google Translate, and image classification is pretty much done today, and things like fraud detection, and even if I came from the airport using Uber, how does it even find me? How do you find the right driver to send to me to ferry me to the place? All behind the scenes you have machine learning algorithms, right? And it's all over the place. And so any questions? Okay. Yeah. All good, or you're bored, or you just want me to start into the math part? Okay. All right. All right. So quick thing about what's coming next. So I think I showed you a lot of things about computational creativity that's going to happen. Cars are going to start driving themselves sooner or later, eventually. I think healthcare is going to be one of the big places where AI hasn't penetrated much, and that's going to be the next domino to fall. And there's going to be a lot of embedded intelligence through robotics, through devices that you're going to carry around, and it will be embedded inside. So I'll just talk a bit about the challenges, and I'm going to rush through and then show you some demos. Well, it's not that it's all a rosy picture. There are challenges, both from the research perspective and also from the societal perspective. So one of the key problems is that the models that you're building, or the machine learning systems that you build, are only as good as the data that you supply to them, right? And if your data is biased, then the models that you're going to come out with is going to be biased. So there is no truth there. It's only an approximation of what input that you provided, right? So I don't know how to, that's a big challenge about how to identify bias, how do you take care of it. It's both a technical problem as well as a societal problem. Then it's very similar. Your models are black box. You really don't know what it is doing. Right? It's kind of related to the bias, but then people will. How do you get more trust in the models themselves? And then there is this whole thing about protecting privacy, and there's a winner take all kind of markets that we are having could magnify the inequality. And if you see the kind of content that we are able to create, then it's very easy to produce fake news and fake content, right? So this is partly it's not a technical. It is a technical challenge to try to detect it, but it is also a societal thing. And I just put this unemployment as a bullet point. I don't buy it, but maybe, who knows? There may be a mass unemployment as machines take over, right? And the second set is about training. So right now, the biggest bottleneck to increasing machine learning capability in the world is the lack of talent that's able to build these systems, right? And partly because we are caught in the middle where the education that we are providing to computer scientists has been more from the point of view of discrete math, more from the point of view of precisely specifying systems, making sure that you don't have bugs and so on. Now, whereas this new paradigm is all about continuous math. All about it's about trying to hack your way through, and coupled to that, the lack of theory that you have is kind of an interesting mix. And things are going to change very rapidly. Yesterday it was TensorFlow, today it's PyTorch, tomorrow it's something else. How do you keep this? How do you produce people who are able to navigate this complexity? Is going to be a challenge. I'm going to skip it quite rapidly. So these are, I'm going to, or maybe I'll just spend some time here because these are all interesting things that you can do purely from the India perspective. Each of these could be a startup idea and you guys can go ahead and solve it. But I think I just added a bunch of things in my, based on my reading of it. Things like law enforcement, like ripe for. So the legal system, defense, plenty of opportunities. That you can go after, right? And health, of course, I touched upon. It was very important, and not much has been done. And things like government and education. So you can pick up any of these areas and then work on all of this too. Okay. Right. So I'm going to stop there, and I'm going to show you a few demos about some of the things, mostly that what we are working on. Most of it is cutting edge stuff. I didn't want to go and do a product demo of all the features that we have in our Adobe products, which does machine learning, but mostly the stuff that we are doing in our lab. Okay. All good? Shall we go? Okay. Okay. So let me. So the first one that I'm going to talk about demo is an idea called deep product search. So this is one of those. It's a computer vision project, and these are the three people who have been working on this. And let me jump to the demo quickly. Okay, the story here is that so often if you are shopping online, right? And then you find something that looks very nice. You just have an image, it looks pretty nice, or you see a magazine, and then you have some photograph over there, looks very good, or you're watching the YouTube channel and you see some interesting piece of apparel, and you want to buy it, right? Or you want to at least know more about it. There is absolutely no way for you to grab that image. How do you search for a look? How do you say that there's a floral pattern with a certain kind of style? It's very hard, right? It's very hard to say it. But it's very easy to just show an example and ask for similar looking products, right? But it's a hard problem because apparel can have completely arbitrary deformations. It can be when you're wearing it versus where you're just taking a photograph of the image of the product alone. It's going to be a huge variation. There can be changes in lighting, right, and so on. So it's a hard problem to identify exactly what the apparel is, and this is what we are attempting to solve here. So I'm going to just choose a file. So I wish I could have shown it on a mobile, because that's the use case here. I just take a photograph of you and then you find the right apparel. But I'm going to do that. So I did something similar. So I went to one of our Marks and Spencer store, and then I took a photograph of something standing in the mannequin. Notice that it's not even a human, it's a mannequin, it's wearing something. And there are all kinds of distractors there. And you do this, and I'm sorry that the server is somewhere else, so it's going to take a bit of time. But 2-3 things will happen. First is, behind the scenes, the algorithm will, from all the distractors, it will identify where the apparel is, right? And then put some hotspots over there. And then when you click on that, then it will tell you what are all the right products associated to that. And if it is in your catalog, then it will get you the exact one. Okay, so it took some time. It doesn't take so long. It's just that it's some server communication going on. So you notice that it identified, it didn't put the dots in an arbitrary place. So it put it on the apparel. And so if you go and click on this, so it did something interesting. So it first of all found out that it was a woman and not a man. So you could have man, woman, child, and so on. So there is a gender classification. And it went inside my product catalog, and then it found all these matches. Notice that all of them kind of match. They're all floral prints. And down here, you find the exact match here. You can actually click on this, and then it will go into the appropriate store. So you can go and buy it, right? Right. So that is that power of this particular search. So it's doing it completely visually, and it's one of the best algorithms out there in the world today. Nothing else beats it. And yeah, so it did age classification, it did gender classification, it segmented the whole image into the appropriate categories that you want, went into and stored all of these things as a searchable index, and then retrieved the appropriate product, right? Yeah. Any questions about how this can?
So,
yeah.
Searching from, did it search the net again?
No. So the question was, where is it finding the products from? Is it from broadly from the internet? No, this is from a certain product catalog that you have, right? So you have a certain retailer who will have a whole amount of product feeds. You can curate that and then place it in a database and then search from that. Good question, yeah. But you could make it internet scale. Yeah. Cool. So maybe just to pause. How am I doing on time? So how am I doing on time? How am I doing on time? Okay. Okay. All right. Huh? Okay. Sure. Okay. All right. So this is the first demo that I had. Then I'll go back to the other demos. Okay, so now I'm going to switch back to the presentation. I just want to talk a bit more about, so this is coming into how we are using advanced mathematics in our research. So I talked about all good things about machine learning, right? All great and all that. Now I'm going to flip the thing and then show you how bad it is really, right? Really, really bad. Just hold on to your seats. Okay, so what's the problem here? So here is almost immediately after the deep learning bandwagon came, so we had this paper from Google Brain which said that they noticed that you can take the image of a bus over there, yellow bus, right? And to that you add a certain amount of noise, very imperceptible noise. So the output is again, you can't visually make out a difference between whether it's an yellow bus and there's an yellow bus, certainly, right? But for some reason, the neural networks, instead of classifying it as a bus, classifies it as an ostrich with 95% confidence. Right? Right? It's amazing. It's like completely out of the imagination how that can be so. But you can imagine the havoc. It's actually an important practical problem, right? So imagine we are talked about self-driving cars, right? They have got to learn, look at traffic signs, and then figure out what to do. Now you can make these. You can actually create some stickers and then place them at strategic points. And from the network, from classifying it as a stop, will say that the speed limit is 45, and it'll just go on. Right? You can strategically create such distractions and then and spoil your neural networks, right? And it's pretty bad. It's not just limited to images. It can include text, audio. There's a paper that came out where you can send out inaudible sounds to your mobile phone and make it do some weird things, right? You can say, okay, Google, do this, and you can. It's completely inaudible to you, but it can make it do some weird things. Right? And you can make it go from any label that you want. Pick any label that you want, and then I can make a noise like that, and add it to that image, and then it can spoil it. So this is the flip side of neural networks, that there is something very strange going on, which we have little understanding about, right? And so there are more examples here. For example, somebody created this adversarial patch where on the top you have a banana. You take a photograph, clearly it's a banana, and you have this just patch that's it's printed out and placed next to the image. Then it becomes a toaster, right, with a high confidence. And you can do something on text classification also. You can change the few words here and there, and make a few typos, and then your text gets classified as something else. And recently, the antivirus companies had malware detection based on neural networks, and you could attack malware detection. You can take this a malware and add some specifically constructed sequence right at the end of the executable binary, and your malware detector will stop calling it as a virus. So it's a pretty scary thought, right? So the question is that how do you deal with this? So the point that we are actually asking really is that, so there is this thing called Clever Hans. It's a library for all generating all these adversarial examples. I went to Wikipedia. I found that it had a very nice story. So apparently, early in 19th century, there was this horse called Clever Hans, which was a rage in Europe. So the claim was that the owner said that this horse can do arithmetic, right? How does it do it? So you say, Hans, what is 8 plus 5? And it'll stomp its hoof, 1, 2, 3, 4, and 13, and then it'll stop. Then everybody will clap. Then you can ask all these arithmetic problems, and then it will solve it by stomping on its hoof. And it was crazy, right? So what happened was, then some scientists came over and then did some controlled experiments, and then they found that the horse indeed had no notion of arithmetic. It was just responding to the audience, right? There are all people, when you come close to the answer, some people will clap, or there will be some expression on their faces, and that is what it was catching, right? It was not really solving the problem. So when the machine, is it that the machine learning systems are not really learning? It is memorizing something which is different from what is there in the problem, and that is why we think it is doing a great job of classifying it as a toaster, it's as a banana, but it's something else that it is picking up. So is it just exploiting bias in training? And it goes even deeper. So there are ways by which you can take a neural network can learn anything. We just talked about it earlier. So you can take a set of data and arbitrarily permute the labels, and it will learn it. It will learn whatever it is to be learned. It will just fit the data. Okay? And so the question here really is that how do you figure out what is the model learning? What is the notion of generalization? So these are open questions and deeper questions which can be only addressed with mathematical tools which we don't possess. So I'm just going to go quickly over some of the work that we are doing in this space. So these are a bunch of people who are working on it. Mayank, Nupur, they're all mathematicians, and I have a bunch of math people from IIT, CMI, and who are working on this. And let me just quickly, so in order to solve this, so there is multiple ways in which you can solve this or try to attempt to get to the bottom of this mystery. But one of the things that we are trying to look at is to look at topological methods to see what is going on here, right? And this is the team. On the right side, you have a bunch of interns. Bishal and Ankita are from CMI. Yogesh is from IIT. And so on. Okay, so let me just jump in a bit. I'll show you a demo at the end of it. So the key thing that I talked about was that it is important to understand the biases in the data. Now the data here is high dimensional. You can't simply view it. You can't just plot it on a graph and then view it and then figure out what it is doing. So you need to have a way to visualize high dimensional data in order to understand if there are any biases. So we will use topological methods to do that, right? So there are two ways to look at data in high dimension. One is through algebraic topology, like figure out what is the homology of that data. The other is through a method called mapper, which essentially comes from the nerve theorem algebraic topology, right? So you want to create a sketch of this data. So I'll go through both, and then I'll connect them to this adversarial example in a bit. They are of independent interest in understanding high-dimensional data. So let me just talk about mapper first. So here, what are you doing here? So your data, I talked about data, which is your collection that's there, and it's a high-dimensional thing. So it's a point cloud, right? It's an n-dimensional point cloud, and it's not a random set. It is usually human-generated data, or there is some physically generated data. So it has some regularity. It's just that we don't know what it looks like. Right? So what you do is that in a standard mathematical way, when you don't know how to understand a certain data, you construct functions from that space to something that you know, study that space, create a homomorphism or homeomorphism or something like that, and then you study it and then try to infer properties of the original space. That's what we do here. So essentially you take a nice differentiable function from your original data space to real line or R2, something that you can visualize. And in this case, there is this point cloud is a hand, which is an illustration there. And then you have, the hand is actually structured in the following way, that there are 5 fingers, and then there is the palm, and the thumb is kind of sticking out in a different way. And then you have your base of your hand, right? So we want to be able to understand this, right? From projections onto some space that we can understand, right? And you can look at the height function, so you can look at the distance. You can label every point in your hand data set in terms of the distance from a fixed point right behind your palm. And if you do that and you look at its inverse image, then you will find that there is a cluster. So if you look at the inverse image of the distance function right at the tip, then you will find only the middle finger coming out. Then as you come closer and closer to the palm, then you will find more connected individual components. And as you come closer and closer to your palm, then you will find one connected component, right? If you can connect them all up in terms of its intersections, then you get a sketch which is on the right side. So this is a way to understand how the shape of the data looks like, right? And at the bottom, I show you another illustration of how the shape of a circle looks like. It's again a circular network, and that produces the hand, right? So this is the mapper algorithm. So in some sense, the mathematical gadget is basically, we are just looking at a nice covering of the original space, and we are inducing some kind of a partial ordering on the cover, and producing a sketch of that, right? And we are claiming that this is a good representation of the original data. And there are mathematical foundations for that. Is the nerve theorem, which says that you can nerve of a particular complex is homotopically same as the space itself if a few conditions are met, right? So this is one algorithm that you are using. And we can use it not just to understand simple 3-dimensional point clouds, but higher dimensional things. So you can directly visualize what is in the data. You can find out how things are bent, and explore the data directly from this summarized view, right? And I'll just give you a quick demo of how it looks like if you are analyzing some real-world data sets, right? Okay, so this is a representation of some data set that we have, and it is colored by a certain activity of visitors to a certain site, and it tells you in one shot what the data looks like really in high dimensions. Let me just try to pull something out. Yeah, it sometimes goes a little weird, or I can just quickly show you in this visual. So this is a better visualization of the same thing, and things have been pulled out appropriately. Yeah, this is the output of the mapper algorithm, and it represents, it's a graphical representation of your entire data set. It's like each point in our data set was like tens of thousands of dimensions. It's impossible to view it or make any sense out of it. But with this, you start making sense, because you now immediately see that there are two kinds of people here. The blue represents a high concentration of certain variable, and red represents a low concentration. And this is a marketing data set, so you are concerned with the number of people who are visiting, the kinds of people who are visiting your site versus people who are not visiting your site. I mean, that's a great concern, right? You have an online business, people come to your site, visit and go away, some people don't. Now I want to know who are the people who are coming to my site and who are people who are immediately bouncing, right? So this is an immediate representation of that mapper. So I can actually go and then select a piece of, if I can just do it, yeah. It's not the, wait, so somehow I'm not able to get this right. Okay, so if the demo would have worked, maybe it does in this. No. So I would be able to select a portion of that particular mapper, and then I will be able to describe it. Let me say descriptor mode. Maybe it's right. So I can color it on different parameters and then view this data set. And if I can just make a selection, oops, okay. Yeah. So this is an output. I'm not able to get that, but imagine that I can select some portions of this and then get a description of what each of these things mean. So for example, here it says it's a mobile app visitor. Right? People who don't visit my site are certain iOS and Android visitors of some kind, and people who visit here are English language browser people and so on. Right? You can understand this in this way. Now, what has it got to do with neural networks? So I can essentially do the same thing on my data set, right? That is coming into it, my training data set, and I can apply this method in order to start visualizing the data. Right? And let me get back to my presentation. Okay. So the other thing that you could do is essentially construct a complex out of the data and directly compute its homology coefficients. Right? So you start with your data set, which is in the form of this 3 circles here, and you draw small spheres around each point, right? And you gradually increase the spheres. As you keep on, and then look at the union of all the points. It's a union of the point and the sphere surrounding that, right? Now, if you see initially, if you draw a very small sphere around the points, it will be indistinguishable from your original data set because nothing is connected to anything else. As you increase the radius, then you will start seeing that some of these points get collected into components, and eventually you will find that there are structures emerging, there are holes that emerge, and as you increase the radius further, the holes start disappearing until you finally get one lump. So there is a filtration, as they call it. As you increase your radius, you keep getting different structures. And each structure you can compute topological invariants of that. And once you compute that, then so this gadget is called persistent homology. What you do is that, so as you vary your radius, various homology components are born, and eventually they disappear. So initially there is no hole, then at some point a hole of a certain size appears. And as you keep increasing the hole, increasing the radius, the hole disappears. So this diagram measures when a certain homology element starts appearing and when it ends. Okay? And this diagram or this gadget is basically a bunch of numbers, and this characterizes your data set. right? And I can take a data set, and just as we did earlier with taking a particular image or something and then computing features out of that, we can take an entire data set and then compute these features, right? And then reapply machine learning on top of that to understand what works and what doesn't work. So you can use it for that question about how do you choose your neural network architecture. It might depend upon your data set, so you could use that to understand what it looks like. So I remember I talked about this adversarial examples. So one of the things that we are looking at, I don't have a demo for that, but we are looking at is that can we look at the space of all those weird looking examples which are just off by a certain epsilon from the original thing, but gives you a very bad output on the neural network. Is that manifold very different from the set of your input images? So that's an example that we are looking at. And so to show that there is a difference, you can look at, so there is a very famous data set in machine learning called MNIST, which is a set of handwritten digits. So if you look at the images of digit 0 that was written by hand and versus the images of digit 1, you do find that the persistent homology is quite different, right? So we can use, essentially these become features for your machine learning program. And this is one of the ways in which we are attempting to solve this problem of machine learning. So, yeah. All right. Okay, and this is my final thing. So I also talked about so it's all in the term of bias and how do I bring trust into the machine learning algorithms. So another focus of research in our team is to see if I can take these complex neural networks, which nobody understands how it's arriving at a certain decision, and can I deconstruct it into a set of if-then rules, right, which a human can understand. Right. So when you're building a model, you'll be able to find rules which tell you how the model is behaving. If you're a user of the model, then you can still get more trust in it. Right. So a quick question or thing about how we are doing it. So a couple of words. So simple models, like if you have a linear regression, for example. Linear regression is interpretable by design because it's just a bunch of coefficients. And if you have features x1, x2, xn, and the size of these coefficients will tell you how important that particular feature is in making your decision. It's straight off easy to do. But the problem is that they are not going to be very accurate. And for accuracy, you have these complex models, and then you lose the interpretability. So the question is, how do I bridge both? And so we call this thing MAGIX, and it's an interesting algorithm in the sense that it doesn't make any assumptions on what the model is. It is agnostic to the model. It's a black box. All I need is that I just need if you're familiar with scikit-learn, it's like you just need a predict proba. So you just need a function which I can pass and input into the model and then get out the set of probabilities. That's all I need. And once I have that, then I'll be able to give you a bunch of rules that describe how the model is working. So let me jump into a demo and then show you how that works. Okay, so imagine that you had a data set. Suppose you had so there is a very famous data set called the UCI breast cancer data set. So it consists of so there is a pathologist who has been looking through a microscope at breast cancer tissue and makes a bunch of measurements about whether there is mitosis going on, what's the size of the cell nuclei, and so on, right? And ultimately, you want to say whether it is malignant or not by some decision that you make based upon these measurements. And the purpose of, so once you have data measured in some way, then you have a gold standard of whether it was malignant or not, then it's an immediate use of machine learning. So people try to create models to predict whether a person has breast cancer or not based upon this data, right? So what you can do is that I can pick up. You just have to input what type of data it is, and I'm going to choose this. So I'll go and choose a file somewhere. Yeah, so it's a CSV file, and I will choose it. Right. So it's exactly the way I described. It's got a bunch of columns. which tell you this mitosis, whether it's nuclei, whether nuclei are there, and so on. And then there's a label at the last column which tells you whether it's malignant or not. Just a CSV file, right? All good so far? Right, okay. And then once you have this, now let's say I have built a model, right, for doing that. Then yeah, I have a model and I can choose the model. The models are serialized, they are written to a disk as a pickle file. I will find out where it is. Yeah, there it is. I got a model. It's a pickle file. So I submit the model and I submit the data set and then I hit submit. And it will start processing at the back end. It will take a bit of time. What we are doing behind the scenes is that we are running a genetic algorithm and some other non-neural net algorithms to understand what's going on. It will take a bit of time, but I'll tell you how it will look like when it outputs. So the output will be a bunch of rules like this, right? So can you see that? So the first rule says that so there are two classes. Class 4 is malignant and class 2 is benign. And it says that if the bare nuclei value, there is a column called bare nuclei, if that value is between 0.5 and 1.5, then predict class 2. So that's a human interpretable proper decision rule. And it tells me that it is 96% precise, which means that of all the data which fits this rule, 96% of the time this rule gets it right. Right? But it also has a certain coverage, right? It covers only, this rule covers only 85% of the data set. So with 85% coverage and 96% precision, this rule is correct. What do you mean by correct? It is correct, it mimics, it's correct in the sense that it mimics the model, right? It doesn't mean that it is actually trying to solve the breast cancer problem. It just says that I have given this model, the model does something, and this rule is following the model with this precision and coverage. And similarly, there is uniformity of cell size between this, and it gives you another rule. So there are two ways. One is that if you have a doctor who has some algorithm, and then you put in a certain patient, and then you get this, you get some value. Then you can look at this rule, and you can tell the patient, well, I have this machine learning algorithm which tells you that you have this malignant or not. Then natural question is, why did you say so? You can't, there's a very natural thing. And you want to be able to tell the patient that these were the reasons why I made that decision, right? Or if you were looking at this, maybe the doctor will say, okay, maybe this doesn't make any sense, so your data is wrong, right? So you have to go back to your data and then build a new model, or your model is not good enough, or it might give you an insight that I never thought about this, right? So these are the various ways in which you can do it. And we can use it in multiple different places whenever you have a black box algorithm and you want to expose it to users, including marketing or any domain that you can. Any questions? No? Okay. So that kind of brings me to the end of it. So I will stop here and I will just say that it's pretty exciting time to be around. Machine learning has deep roots, founded with foundations in mathematics, as for everything else, and there is a ton of work to be done to understand how these things are working. What are these gadgets doing? It's important from a business perspective, from a social perspective, as well as from a technical perspective. And once you do have a better understanding, you'll start improving the algorithms even better. So I invite you all to start exploring this field and reach out to me if you are looking for some internship opportunities or generally want to explore this field. Thank you very much. Yes.
So the MAGIX thing, the last one. So you're kind of using machine learning to understand machine learning.
Yeah. So perfect. Great question. So I like the way you're going. I was debating. So there is a whole bunch of other fields that we are working on, which is called learning to learn, right? So it comes close to what machine learning, what the question that you're asking for. Yes, indeed you can. One of the research that we did was the following, that there is a process of machine learning, the back propagation algorithm we saw, right? So we wanted to observe if there is any regularity at all in the way the algorithm learns, right? And whether it can be extended further. So it's a paper called Introspection Network, you can look that up. What it says is that we build a neural network that observes the way another neural network is learning, right? And essentially gets the essence of that. So it figures out what are the patterns of weight evolution over time. And very interestingly, it learned on some very simple task, and it's able to transfer that learning to completely new tasks. So we started with a network that learns about image classification of digits, and then you apply it to some really humongously deep network which is doing some other task, and it's able to accelerate the learning significantly. In some sense, what you're saying is, okay, the machine looks at this, and then your learning is humming along, and then you say, okay, now I know exactly what you will learn 100 steps down the line, so let me just tell you where you're going, right? So that is one way of applying machine learning to understand what machine learning looks like.
What it basically does is accelerates the learning rate.
Yes, yes. What was is there a different perspective that you're having?
No, I wasn't expecting yes first.
Okay. So yes, so that you can do that, and that's an interesting area of research. Recursively apply machine learning. Yes.
You said that, for example, persistence homology is a way of taking your raw data and then turning it into something that's amenable to machine learning, right? Yes. So are there a lot of other such ideas out there?
So,
I mean, this is for images, right?
No, it's not just for images.
Okay.
It could be any point cloud.
Okay.
Right. So I took this example of images to make a thread of, try to make a story out of it. But the real uses of this persistent homology is in data sets that are not images, which are marketing data sets. So, for example, I know the behavioral data of a person who's coming on the website and then doing a hovering action, and like goes to this site, and so on. Maybe they're making up their mind to purchase something. So if I can, for example, look at each person as a point cloud of interactions, and then I can look at persistent homology, for example. So that's it is spatial data. Yes, it is spatial data. Yes, you need it to embed into some RNs. It needs to be embedded into RN. The other would be if you just had a graph. The other kind of data is just a graph, social network. That's another open area of research. A lot of work happening. Two ways to do this. How do you do deep learning on graphs? And how do you? And there's a new field called geometric deep learning. That is coming up, where if you look at manifolds other than Rn, then are there different algorithms? So instead of gradient descent, so for example, you can try to you can embed your data set into an hyperbolic space, and the very interesting work where the gradient descent takes a slightly different form, and it will produce embeddings in a different space. Yeah, so there are things happening on the research side, but nothing from those have come into production yet.
I only asked because I sort of see closest to what mathematicians would be doing. So. Okay.
How much do you interface with social scientists?
So not too much, unfortunately, and I would like to do that because so the social scientists. So I try to take a data-driven approach. So if you have data sets, then it will be very useful to look at the social phenomena from a data science perspective. Social scientists per se, I mean, can you give me more clarity on what you're looking at?
Sure. So like what the kind of things I had in mind, like for example, I don't know if it's happening in India, but in the United States, they use these kind of data-based approaches to incentives given to teachers in public schools. And but the very parameters you're measuring and the way you're making your algorithm, it's missing some important.
Yes. So there is a very nice book by somebody called Cathy O'Neill.
Exactly, that's what
Weapons of Math Destruction, right?
Exactly, yeah,
right. Yes. So that was in fact one of my inspiration to looking at this model interpretation of that, and that was a very valid point. So it's only your machine learning models are only as good as how you're measuring them, and there will be all kinds of biases. And so in this work, we actually looked at some data sets from social science. So there is an employment. There is a data set of, it's a US data set. It tells you about how somebody was promoted or not promoted. Race was never a parameter in that thing, but the algorithm, but somehow the promotions were all skewed towards one race, right? So and now you perpetuate the same biases again and again, saying that it is a data-driven approach. We know exactly what it is. So, but you can't wish away data. From data-driven approaches. You cannot wish it away. So the only way is for us as mathematicians to enter into it and try to clarify exactly what is going on and try to give do something. Maybe interpretation the way I presented is a way out.
Or maybe just work together with social scientists who are watching out for these kinds of phenomenon, and data which is people who are making data are aligned with people who are more sensitive to other issues which are going on in society.
So most organizations now have a chief privacy officer, a chief ethics officer. I mean, you probably will have institutional review boards and others too coming up to make sure that you have, after all the Facebook problems, and there is also in Europe we now have what's called the GDPR. Right? So you must have seen that nowadays all your websites are sending you emails that we have changed our terms and conditions and so on, right? So people are getting more and more sensitive about how their data is used, what's going into your algorithm. So there is a whole field called data governance. So when you're collecting data, then what you should use for modeling and what you should not use for modeling. They're all important aspects that one should take into consideration. Yeah, but from pure, can you finish? Sorry, I didn't interrupt. So that's one aspect of it. There is also other interesting aspects of using data-driven approaches and using social sciences is to quantify behavioral economics and try to nudge people into doing the right thing. And that is also an interesting approach. And third one, this is purely from a research perspective. We have an interesting project where we are trying to see what it takes. For example, if you have a prisoner's dilemma kind of situation, where the equilibrium is a Nash equilibrium, the natural state is a Nash equilibrium where nobody cooperates. But a cooperative system is something that has a higher reward, but it's a very unstable place. So how do learning systems evolve to get to a better state? So maybe social scientists have an input in designing such systems.
Anybody else has anything to ask? Okay.
Sort of maybe
wrong question from but I just want to know that the machine learning seems to be solving very fast problems which traditional computing doesn't seem to be able to solve, right? So Do you think that we need a new way to think about computational complexity itself in the context of machine learning, or will the old kind of things work?
Great question. So computational complexity, so you have this complexity zoo and you have all these things. So the closest thing that comes to me is the randomized algorithms, right? So they always seem to get better at this. Beyond, so I don't think we have approached this problem in any rigorous way to quantify what exactly is it. So there are a few notions of complexity. There is this BC dimension theory that was there a long time back, but the bounds that you get are ridiculous. It doesn't have anything to do with reality. Maybe it's a physics question rather than a math question, because you're talking about complex systems. You're talking about phase transitions. It's probably a physics question rather than a math.
Thank the speaker again.